Hello and welcome to this introductory lecture of the class Stabilized Finite Element Methods for Computational Fluid Mechanics. In this introduction I'm going to cover all the usual stuff. I'll talk about the setup of the course, so the course structure. I'll talk about the grading. And I'll talk about the course content. And I'll start with the course content, and I think the first thing that I should talk about is why we want to do what the title of this course says. Why do we want to use finite element methods for computational fluid mechanics? So I'll start with a bit of an example. So this was a simulation that we ran a little while, a couple of years ago. And what we're seeing here is a sign structure. So this would be a sign that would stand by the side of the road. And this was actually ran in Minnesota. And the Minnesota Department of Transport found that these road signs were fluttering too much in the wind. And of course there's all kinds of restrictions on safety measures of how strong a road sign is allowed to be in case there's a collision with a car. So they didn't want to stiffen or strengthen the sign structure, rather they wanted to optimize aerodynamic shapes. And that's when they asked the University of Minnesota to have a look with them and see what could be optimized. So in our research group we focus on finite element methods, and naturally we used a finite element method for handling this problem. Now that is not very usual though, because if you're slightly familiar with computational methods for fluid mechanics, then the method that we typically would use is a finite volume method. And so I think the first question that kind of arises based on the course title is, why do we not use a finite volume method, but why do we rather use a finite element method? Or would we rather use a finite element method? Now I think this is a very long-standing debate. In industry, finite volume methods currently dominate. This is largely due to historic reasons. It's been like that for a long time. What we see though is we see this gradual shift toward finite element methods. And I don't want to go into this debate too much, because it's still there's still differences of opinion on this. But what I can do is put forward some arguments for why we might want to use a finite element method for handling these kinds of problems. So why a finite element method? Well, one of the things that I would also really like to emphasize throughout every one of the lectures in this class is that the finite element method has an extremely strong mathematical background. And the mathematical background that I'm talking about is that of functional analysis. That's where it has its roots. And this gives us all kinds of analysis tools for the stable nature of the finite element scheme, the well-posedness. And these theories have been developed for a very long time. So the finite element method is much less a pure numerical discretization approximation technique, and it's much more based around a much more global field of mathematics. Now, of course, as a researcher I find that an interesting argument, but your boss in industry might not, so we need some practical arguments as well. And the argument that's typically put forward is that it's very, very difficult for a finite volume method to be of a higher order. And what higher order means is that once we start to shrink our mesh size, so we refine our mesh, then our error decreases, and the order at which it decreases, that is the order of the scheme, of the numerical method. And it's very difficult for a finite volume method, because it kind of depends on a regular structure of the grid, to be higher order. And specifically that's very accurate if we want to represent our geometry accurately. And typically we have geometries of relevance that are not boxes. We probably have smooth surfaces, so that we want to accurately model the surface of our geometry. And once we try to do that, finite volume methods struggle with getting higher order schemes. And finite element methods, we are actually quite familiar with meshing arbitrary shapes, and we can use any order polynomial basis. Yeah? So it's pretty straightforward for a finite element method to be higher order, also in the case of fluid mechanics. And it turns out that for fluid mechanics, it's actually very important that we use higher order methods, because we have all kinds of interesting flow structures, vortical structures, certain eddies, that we'll all talk about in later lectures. And these need to be represented and need to be represented well in order to be maintained throughout time, because else they will dissipate too fast, they will disappear, and these actually have a huge impact on the complete solution field. Yeah, so higher order methods are particularly important for fluid mechanics. Finite volume methods struggle with these, finite element methods do not. And what we see is a gradual shift, especially in research codes, towards finite element schemes. Now another argument is that of multiphysics. In many engineering relevant cases, we are not exclusively interested in fluid mechanics. They might be coupled with other equations. And I actually have two examples here. One where the fluid mechanics is coupled with solid mechanics, so we have some fluttering airfoils in this case. It might be from an aircraft, in this case it's from a wind turbine. And actually the picture on the right also deals with this. This is from actually a COMSOL website, where it's interfaced with the heat equation. So we're interested in transporting heat. And so then we have multiple types of physics, and even though the finite volume method is very good at handling fluid mechanics equations, we typically don't use the finite volume method for solid mechanics. That's where finite elements dominate. So finite element methods have the strength of being able to handle all kinds of equations, and in this sense are very suitable for multiphysics applications. Now here I have another example of, this was during a conference in 2012, so it's a while back, but I think the trend has maintained, where the conference organizers posed a couple of research questions. So they had a couple of challenges really for certain simulations. So in this case, on the bottom of the slide you can see an airfoil, and they tasked multiple research groups of computing the flow around this airfoil with their computational tools, so the codes that they have in-house. And even though I don't want to go into too much depth of what we're actually seeing in these graphs, so these in general these are the arrow graphs, and we see these are all arrow graphs. On the y-axis, and on the x-axis we have different measures. We either have the mesh size, but we also see some computational expense. So they were interested in how the different research codes performed. Now I don't want to go too much into the performance per se, but I would like to point out that if we look at the type of technology that these research groups were using, then we find that finite volume methods are relatively underrepresented, and finite element methods are highly represented. And this is kind of what I meant before, that especially in research codes, we're slowly shifting toward finite element implementations. And typically industry is lagging behind research a little bit because they need to use methods that are proven, while we're currently at a stage where finite element methods are starting to be proven. So in our research group, we're expecting that in the next 5, 10, 20 years, we see also in industry a gradual shift toward finite element methods for fluid mechanics applications. And in some industries, I'm sure they already do this, right? COMSOL was an example of an industrial code that uses finite element also for their fluid mechanics applications. So with the part of this class is that you could get ahead of the curve here and get some knowledge on the use of finite element methods for fluid mechanics. Now specifically the finite element method that we're seeing here is discontinuous Galerkin, DG. And this is also one of the methods that we will talk about in this class. So last year the name of this class also included discontinuous Galerkin in the title. I've removed that because in a very general sense we can also think of discontinuous Galerkin methods as a stabilized finite element method. So I felt that stabilized finite element methods was already sufficient and had a bit of a shorter title. But DG will be one of the important parts of, or the larger sections of the lecture series. Okay, so that's kind of all I want to talk about in terms of finite volume versus finite element. If you would talk to someone whose research focuses on finite volume methods, then they will give you other arguments. So that's not really a debate that I want to go into much more throughout the rest of this lecture series. So I gave you the arguments that I have in favor of that, and that's kind of all I want to do in that regard. Now, you might still have a question though in terms of finite element methods for fluid mechanics, and it kind of depends on what background you're from. If you're from a solid mechanics background, and I kind of expect that most of you are, then it might feel kind of strange to use finite element methods for fluid mechanics applications. And I think that this kind of this feeling is rooted or is based on the way that finite element methods are taught at an introductory level, and that is again based on historical reasons. So historically, the finite element method was developed in the field of solid mechanics, structural mechanics. And we see this throughout all the nomenclature in finite element methods. We have a force vector on the right hand side, we have a stiffness matrix and element stiffness matrices. And if we have this force lumping at the boundary. And all these terms, they kind of focus around solid mechanics. Let me take the example of this stiffness matrix again. So even if we solve for a Poisson equation, which might represent a temperature field, we would still call the matrix that we assemble the stiffness matrix, even though stiffness has nothing to do with this temperature problem. And that is because of this historical reason of the finite element method being developed for structural applications. And this also shows very strongly in the way that we teach finite element courses at an introductory level, in the way that we explain different element types. And I have a couple of them on the slide here, where in 1D we might think of our one-dimensional elements as either springs or beams. So we have this very strong tendency of fitting in things that as a structural engineer we're used to in our way of thinking about finite element methods. Yeah, and also for not only for 1D, but for multi-D, 2D or 3D elements, we kind of try to think of them as spring-like physical volumes or physical materials that have a stiffness. So how does that then translate to fluid mechanics? Well, a fluid doesn't really have a stiffness. So what we're gonna have to do is we're gonna have to represent certain fields. Yeah? So in solid mechanics we have maybe a displacement field. So every node has a displacement. But in fluid mechanics we don't have a displacement of a node. What we have is a complete field of pressure, a pressure field, or a velocity field. And then what we're not doing is we're moving around every node every time step. No, we're keeping the same mesh, and we have a velocity field that is overlaid on that mesh. So this might all feel a little bit inconsistent with what you've seen before, and I think that that is because the introductory way of finite element methods is very intuitive and very understandable, especially coming from an engineering, structural engineering background. But it's also a relatively narrow perspective, and one of the things that I also hope to teach you in this class is that there is an overarching perspective, and that is where we do not think of elements as either spring-like one-dimensional pieces of solid, but rather the elements are nothing more than a bunch of shape functions. And if we exclusively think about these shape functions, then we can represent any solution field, like a pressure field, a velocity field, temperature field, as just a summation of these different shape functions multiplied by coefficients. And then we can represent a whole bunch of different functions. So that's what's showing here on the right. Yeah, so U is this sum over the number of degrees of freedom of coefficients times functions. And these functions, well, they are based around this tessellation of our geometry by a mesh of elements, and that's where they are defined. But in principle, they could be anything. You could use trigonometric functions here, and you would get a spectral method. You might have functions that have very global support. That's what we see with reduced basis methods that we talk about in the modular reduction course. Yeah, and specifically for finite element methods, we typically have these localized shape functions that are also illustrated here, defined by these elements on a mesh. And that is almost the exclusive way that we're going to think about our elements. They are merely a tool for creating shape functions. So we're not going to think about them as blocks of material that have a certain stiffness. No, we're going to think about them relatively mathematically as just a framework for building shape functions, such that we can write some arbitrary function u as the sum of coefficient times these functions. Okay. So then throughout this class, the thing that we're really trying to do is we're trying to solve the Navier-Stokes equations. And I'm not going to introduce these yet. I'll get back to this in a different class. But the point that I would like to get across right now is that these are relatively complex equations. There's a millennial prize around the Navier-Stokes equations. So if you can prove their existence, unique existence in time, and a certain smoothness, then you'd get $1 million US. Yeah, so these are very complex equations. And we can highlight a couple of parts of these equations that make them so complex. So that's maybe something I'll do already, and we'll get back to this again in future classes. But then I'll already have a bit of a feel of what might be difficult here. Yeah, so one thing that we're seeing in these equations is that, well, there are really two equations. And this makes them, and we have also two sort of different solution fields. We have a pressure field and a velocity field. And if we have two solution fields, then this makes this a mixed problem. And we'll use mixed methods for that. Now the second thing that is a little difficult here, let me emphasize that a little bit more. So we have here a pressure field and a velocity field. Yeah, so that has to do with this mixed nature. Now what else do we see in these equations? Well, the one on the right here, it might look a little tricky, but actually this is a little bit more like diffusion. And diffusion is something that we're able to handle quite well with the finite element method. So that part is actually not so tricky. Another tricky part is that we have this nonlinearity here. So that's something that I have to handle. And the last thing is that inside of this nonlinearity, we have a term that we call an advection term. And the advection term, that is something that is very fundamental in fluid mechanics. We have this transport by means of a velocity, that's called advection. And that is actually something that the finite element method specifically struggles with quite a bit. And that's where we'll see all kinds of instabilities. Also for the mixed method, we're going to see instabilities, and also due to this nonlinearity, we're going to see instabilities. And these are all things that we're going to have to stabilize, and hence the name of the course. Now, I guess, even though I'm saying that, I would also like to emphasize that this is more general than fluid mechanics. This equation lends itself really well to having to teach about instabilities and how to remedy those instabilities. But everything I'll say is much more general than the application of fluid mechanics. We also can see instabilities in solid mechanics or even for heat equations. So wherever there's a connection, I'll try to emphasize this a little bit, because I would like you to appreciate the more general notions that I'm talking about. Fluid mechanics is particularly sensitive to these instabilities, and they occur very rapidly, and that's why I'm focusing on that field of mechanics in this lecture series. Okay, then a bit of an overview of the course content. So I took this slide from last year's lectures. And this is not set in stone, and of course that is because this year we have to do things a little different than last year. And also I decided to do things maybe a little different than I did last year. So please don't look too much into the details here. Specifically the way that homeworks are set might change a little bit. I think I'll also be a little bit more flexible in terms of the actual lecture hours. I'll get back to that in a second. So I'll use this slide mostly to talk about the content of the course, and we'll get back to the structure in a second. So the content of this course kind of structures around precisely the three difficulties that I emphasized in the previous slide. Yeah, so we have these three parts of these equations that are difficult. There's the advection part, the mixed nature of the equations, and the nonlinearity. And that is also roughly how I'm going to structure this complete course. So in the beginning, we're going to talk about the advection. Then we have a whole bunch of lectures on the mixed part, the mixed nature. Then we have these lectures on discontinuous Galerkin, and they kind of are both of these. And then towards the end, we're going to talk about turbulence modeling and variational multiscale. And this really has to do with handling this nonlinearity. So the course is structured in 3 or 4 blocks that each deal with a particular difficulty of the Navier-Stokes equations. And I don't want to jump right into the Navier-Stokes equations because they are very tricky. Rather, what we're going to do is we're going to pick apart the Navier-Stokes equation into these different difficulty levels. And for each of these difficulties, we'll find a simplified equation that represents specifically that challenge, either the advective challenge, the mixed challenge, or the nonlinear challenge. And then we can analyze that equation a little better, and we can understand why this is a problem, and we're going to talk about how to solve something like this. Yeah, and by doing that for each of these different difficulties, then towards the end we'll end up with being able to handle the complete Navier-Stokes equation as a whole. And that's actually the first thing that I'll start doing after I finish this lecture. So the next lecture is going to be about separating the Navier-Stokes equation into these different prototypical equations, is what I'll call them, that each represent a particular difficulty of the Navier-Stokes equations. Now then there is still a little bit of a gap here, and that is on functional analysis. So this is going to be the mathematical preliminaries of everything else that I'll talk about. Yeah, we're going to have to analyze these prototypical equations. Well, maybe this should also go up here. And with this I mean that we're going to have to build our tools, our mathematical tools for understanding where these problems come from, because we first need to understand where these problems come from before we can try to solve them. And in order to understand where these problems come from, we need to develop a bit of a mathematical Swiss Army knife, if you will. So we're going to have to develop some tools, some ideas on how to define an instability, for example, how to know if a finite element method is well posed and what that might mean. So we're first going to talk about some of this math in order to handle the prototypical equations, to analyze them, and after that we're going to talk about how to solve the problems that we then identify. Now you also see that last year I had a couple of homework rehearsal lectures. So that was a full lecture where I would give the answers to the homeworks and we would discuss these. I'll kind of have to see if that's still something that is useful right now, given the new setup of the class. Okay. Yeah, and this is also something that I'll talk about in a second. I'm not sure if there's going to be 9 homeworks. I do want to keep the 60% versus 40%. In terms of grading. Yeah, okay, I'll get back to that in a second. So then the learning objectives of this class. Well, the title of the class is that we want to handle fluid mechanics problems with the finite element method. But as I hope I've been able to emphasize now already a couple of times, this is not really what I want you to take away from this class. I want you to take away much more the analysis tools that we're developing in order to understand why we need to handle certain problems and where these problems come from. And this then focuses around the use of stabilized methods, discontinuous Galerkin methods, this mixed method, right, pressure velocity pairs, and fine scale modeling. And so I find the content in that sense much more important than the background that we're actually talking about fluid mechanics. The second thing that I want you to take away from this is the language of computational mechanics, is the way that I wrote this down. And I feel that after you take a couple of classes on finite element methods and computational mechanics in general, then you're still a pretty long way off from being able to read research papers. And well, since we're in a university and since you'll have to do a literature survey and a master thesis afterwards, you will be exposed to these research papers. And when I started moving towards more research-oriented work, coming from also my degree in actually solid mechanics, I found this still to be a pretty wide gap, and I can show you some examples here. I've took some screenshots of some arbitrary papers where you see that they're relatively math heavy, especially if you're going to talk about actually finite element theory. You see these curly braces. This will be a set definition, and these are different function spaces. Well, hopefully this is something that we're slightly more familiar with. These are weak formulations. Let's go one further. Then we see a whole bunch of these jump operators. This is a different way of writing these weak formulations with these brackets to shorten things. One more further. Then we see a whole bunch of these subconditions, inequalities, different parameter estimates, more inequalities. So we see a whole bunch of things that are relatively complex, and that I anticipate right now that if you would go through a paper like this, you'll be quite lost. And that's another learning objective here, that I want to familiarize you with, at the very least, some of the notation that you'll come across in these papers, yeah? So that you feel a little bit more sure-footed once you go towards a master thesis in this direction. Then also this broader perspective on the finite element method is something I really hope to get across, right? So rather than thinking of elements as blocks of stiff material, we can think of them as just a tool work, or the tool for the framework for defining shape functions, and that our solution is just represented by a weighting of different shape functions. And this is a broader perspective that I think that every computational analyst should be aware of. And lastly, the finite element method, or the finite element analysis in general, is not a plug and play tool. And that is something that we might mistakenly feel if we only take introductory classes in finite element methods, because then everything tends to kind of work quite well. There's reasons for why things work quite well for solid mechanics problems and for heat problems. Now, once we go a little bit deeper into finite element theory, then we already, also in solid mechanics, we have these notions of locking. So then we already kind of realize, okay, sometimes we have to be a little bit careful in the way that we handle things. And specifically for fluid mechanics, that is actually a big deal. If you're not careful, you're going to get wrong results. So I think that's going to be another learning objective here, is that you kind of develop an appreciation for your job as a computational analyst, of being able to understand that if you solve a problem using finite elements, that doesn't immediately mean that you get the right answer, right? So you have to think a little deeper. And I think you really gain that appreciation from fluid mechanics applications, because there things just really don't work unless you do it properly. Yeah? So that's something that I hope I can convey, and that you'll also be able to take with you for all kinds of problems, not only fluid mechanics problems, but just in general, that you are a little bit more careful in the way, or a bit more skeptical in your results, healthy skepticism, and in general realization that things, even though they might look nice, that doesn't mean that they are nice. Yeah? And I'll actually give some examples of that right now. So I have two examples to illustrate this point, and these are examples that I'll also talk about in future lectures, and then we'll analyze these results and we'll try to come up with a solution. For now, I don't really want to talk too much about any of that. I just want to give you a feeling of the types of things that we'll see later and of what I just meant, that sometimes using a finite element methods, things just do not work the way we might think they would. So here we have a Stokes equation, and a Stokes equation is a Navier-Stokes equation minus a couple of the terms, and essentially that comes down to you'll be able to use the Stokes equation if fluid moves, or air or water or whatever moves very, very slowly or is very viscous. Now we'll get to this as well later. So it's a simplified version of the Navier-Stokes equation, it's very simply put. And this is a very classical benchmark problem, the lid-driven cavity problem. And what it is, it's really just a square, and all around the sides we have a boundary condition for U, one of our solution fields. Yeah, so we have two solution fields, we have this mixed problem, we have U and we have P, and we're trying to find both fields, we're trying to find solutions for both fields. So our velocity field and for our pressure field. And our boundary conditions are such that we say that the velocity is going to be 0 around these sides of our domain. Yeah. And typically we need to set one point where we set a pressure, and that kind of has to do with that the only way that the pressure shows up in these equations is via its derivatives, which means that you would always be able to add a constant and it doesn't change the solution. We'll also see this later, but I guess what I'm saying is just that we have to put, at least at one location, we have to set the value for the pressure, else it's not a well-defined problem. And the last condition is that at the top, at the lid, we have this flow that is exclusively pointed towards the right, so we only have a ux component, so uy is actually 0. So this is, the flow is driven to the right, sort of in a shearing sense. Yeah, we're kind of shearing the flow on the top. So what does the solution to something like this look like? Well, we would get something like this. And we get the circular motion of fluid, because we have this shearing force at the top, so it's gonna flow like that. Oh. And we get certain pressure concentrations or peaks at these tops. Yeah, because of course there's a unit flow here in this direction, and then it's 0 here, so there will be a concentration of pressure over there. So now, why am I talking about this example? Well, I want to solve this example with a couple of different finite element methods, and I have a couple here, and because my face is overlaying part of the slide right now, I had to move down one of my element shapes, and I see that I'm also cutting some of the title. Well, the title of this slide says, which elements, velocities and pressures belong together? And what I have here is I have a couple of different pairs of elements, and I have a couple of different solution fields. Okay, so let me take one step back here. What do these element pairs actually represent? So we see here two elements here, one element here, and we see black dots and white circles. So the black dots are degrees of freedom for the velocity, and the circles are degrees of freedom for the pressure. So we have a mesh consisting of a bunch of elements. These elements represent shape functions in very much the way that you might be familiar with. So we have these head functions. And we have different degrees of freedom in each element that either go towards the velocity field or towards the pressure field. So we have a whole bunch of choices here, and this comes back to this mixed method, right? So we're trying to solve for two fields, a velocity field and a pressure field. So we're going to have to use a mesh and elements and shape functions for the velocities, and we're going to have to use mesh elements and shape functions for the pressures. And of course we can combine these in a whole bunch of different ways. And now it turns out that if we combine this in an inappropriate manner, then we can get solutions that look pretty terrible, right? So here we have different pressure solutions, and here we have different velocity solutions that correspond to some of these elements at the top. Now, at this point, I haven't matched this up yet. So the elements do not correspond to these pressures, and these pressures do not correspond to these velocities. And if I would be standing in front of a classroom, I would now start a discussion on whether or who thinks that what element corresponds to what pressure corresponds to what velocity. So I think I'll encourage you to pause the video right now and try to think of that yourself. So let me restate the question here. We have different pairs of elements, combinations between pressures and velocity degrees of freedom at the top. If I use those as my elements in a mesh to handle the previous problem, this guy, then I get the solution fields that you see at the bottom. And my question to you now is to match the elements with the pressures and the velocities. So you can pause right now and also skip to the next slide and I'll give you the answer. So here these are matched, right? So now they're in the right order. This element corresponds to this solution, pressure and velocity, and these correspond like this. And what we can see is, well, the main takeaway message here is that if you do not use the proper combination between these meshes or these element pairs, then you get solutions that are pretty horrible. Yeah, and I'll go over each one of these one by one to kind of point out some things. So if we use the P1, P0 element, which means that for the velocity we use a P1 finite element, so we have this nodal finite element on each of the nodes of our elements. And P0 means that in each element we just have one shape function that is a constant value in that element. Then you would get a solution like this. This is complete locking. You see that we don't even have any kind of solution field in the velocity. I think anything that you might see over there is sort of numerical error. This is noise. And also in the pressure field you see that this is also just complete garbage. Now how could you have known this? This is pretty much, if you go back to the previous slide, go a little too fast. This is the only one where you can see these constant triangular values for the pressure field. Yeah, so this is all the other ones don't have constant values on each triangle for the pressure. Yeah, so that's something you could have noticed. So then the next one, this might already look a lot better from the velocity perspective. But we still get a garbage result for our pressure. Yeah? So now we're using P1 elements for both the velocity and the pressure. So this is actually quite interesting to me. I found it quite interesting when I was running these simulations that the pressure is so bad, right? This looks nothing like the true solution, but nevertheless our velocity kind of looks the way it should. I mean, there's clearly still some defects here, but it's not by any means it's not as bad as the pressure field. Yeah. So then the next one, where we have a Q1, Q0. Q means that we're dealing with square elements rather than the rectangles or the triangles. And 1 means again that we have this first order P1 or polynomial order of 1 nodal finite elements for our velocity, and Q0 means that we have per element constants for our pressure field. So that's also something that you can see again in the pressure solution. So this one looks already a lot better, but this is still a defect in the sense that there's no smooth transition in the pressure field. We have this up and down jagged pattern. So we could have had something that looks much more like this. But it doesn't look like that. It has this up and down nature. And that's called a checkerboard pattern. Yeah, we'll talk about this in future lectures, and we'll see why this happens. So it looks sort of okay, but that's still not something we're happy about. And in different cases, in different geometries, whatever, this checkerboard pattern might be much more pronounced, and they might not recognize the solution field from this solution on the left. Nevertheless, our solution field of our velocity is really good. So this is again this funny combination where our pressure might not be optimal, but our velocity actually is. Now then we're going to, is this the last one? Let me check. Yeah. So this would be the element that we typically call a stable, element. This is the Taylor-Hood element. For this element you can actually prove that both the pressure and the velocity behave in a way that we want them to behave. Yeah? And in order to do this, we first need to understand what actually drove the problems that we saw in the previous slides. And that's one of the things that we'll do during our analysis lectures. Yeah? So first we try to understand the problem, and then we're trying to solve that. The Taylor-Hood element is one technique for solving this problem where our pressure might have these spurious pressure modes, is what we call this. So that's the first example. Then the second example. Now I am using the complete Navier-Stokes equations, and this is also a very classical benchmark problem. And this is called a channel flow problem, where we essentially have just a sandwich structure of a plate on the top, a plate on the bottom, and then we're driving a fluid, a viscous fluid or a less viscous fluid, in between those plates. And people have done this with very high mesh details, so a very highly refined mesh, so that we have an idea of what this should look like. Come on, I don't mean to do that yet. Yeah, there we go. So I'm also running this computation, but now with a much coarser mesh. And what you can see is that as I'm running this computation and flow is kind of being pushed in between these plates, we see that the color here becomes increasingly more red. And if I then compare that to what it's supposed to be like, so on the left I now have a cut plane, which I took from literature, someone who solved this problem with an extremely refined mesh, and they're saying, well, then the mean flow should look like this blue line. And if I then take a mean flow in the solution that I ran over here, then I find that I overpredict the mean flow by over 50%. And these are again the mesh nodes here. So the nodes of the mesh. And I didn't do anything wrong per se here. I used a right element pair, what we talked about in the previous slides. I used the right kind of stabilization for the advective term. Talk about that later. I used the correct turbulence model. So I did everything correct, and still I'm getting this 50% mismatch between what I'm obtaining from my computational solution and what it should be like. Now that's a pretty big mistake. Suppose that you're designing a cooling installation where the flow is cooling these two plates, or this is somehow important for the injection of combustive material, then an overprediction of 50% is quite significant. And if you tell your boss that the amount of flow flowing between these plates is 50% larger than what it's actually going to be, then we might run into problems, right? And again, I did actually not make any mistake here. Nevertheless, I'm getting a solution like this. So that's, I guess, the point that I've raised before, that fluid mechanics applications are very unforgiving. And we really need to know what we're talking about in order to get solutions to behave in the way they should behave. So let's try and analyze this very briefly, and I'll get back to this also in later lectures, but I kind of want to give you an idea of how we might go about talking about these kind of problems. So here we again have the Navier-Stokes equations, and what these equations really are, at least the second set of equations, these concern balance of linear momentum. And if we then take a look at the problem that we were solving before, we have a plate at the top and a plate at the bottom. and I have a certain force driving it to the right, that might be, I don't know, a pressure differential or whatever, then the only way that we get a balance of linear momentum, so a steady mean state, is if we have this opposing force, and the only way that we can have an opposing force is by this slip across the boundary here. So we have this shearing effect, that the flow is shearing across the boundary, that's producing a shear stress in the opposite direction as the flow, and at some point the shear stress should balance with this pressure that is driving the flow, and once we have this balance, then we have balance of linear momentum, and that's where you would get your mean flow prediction. Now clearly, by doing what we're doing here, we have this complete overprediction of our mean flow, meaning that we have a much higher flow at the point where we have this balance between the shear stress pushing the flow back and a pressure differential pushing the flow forward. So when does this balance occur? Well, in order to understand this, we have to kind of understand a little bit what the Navier-Stokes equations are comprised of. And I'll talk about this in future lectures as well, but the key point here is that we're dealing with Newtonian flow. And what the Newtonian flow is saying is that the shear stress is proportional to this the gradient or the derivative of the velocity in normal direction. Yeah, so my shear stress along this plane is proportional to the derivative of the flow in this direction. So now, then suppose that I have this very coarse mesh, which means that my first degree of freedom away from the boundary is going to be here. And this shear stress is going to be the derivative of my u with respect to that height. So if I have a very coarse mesh and I have my solution here, suppose that it's a flow that looks something like that, then my derivative is going to have this steepness. And I kind of hope that the idea of what I'm trying to say here is clear. Suppose that for the true solution, the blue one, in order for this force to balance with the shear stress, I would need to have a shear stress that corresponds to a slope that is this steep. And in a true solution, I might have something that looks like this. But with my coarse mesh, I cannot represent something that looks like this. At best, I can represent something that looks like that. But this won't have the right slope, and hence will not have the right shear stress, and hence will not produce a balance of linear momentum. Rather, with my coarse mesh, I need to have my first node have a velocity that's all the way like that in order to have the shear stress that balances out with the applied load. And that's where this complete overprediction of our flow comes from. So this might be the true solution with the right shear stress. In order to have the same shear stress on a coarse mesh, we would have this huge overprediction. And that's kind of what we're seeing here in the true solution. So if I would zoom in here, then I would find that the blue line actually has a much higher slope. It's much steeper at the very close to the boundary layer, or very close to the boundary, in the boundary layer, than what we're seeing in the orange line, where the first line is here. Okay. So what would be a solution strategy here? Well, that's going to be pretty tricky. We don't want to mess too much with the equations. But this is the first time I'll talk about a little bit about discontinuous Galerkin methods. Because what we're doing with discontinuous Galerkin methods is we are allowing more flexibility to our finite element scheme. And specifically what that means is that we're releasing certain constraints and we're reapplying them weekly. So we're giving a little bit more flexibility. So on the left here I have the same simulation that I ran a second ago. On the right I have one where I'm using a discontinuous Galerkin type, a method where I'm allowing now flexibility on those boundaries. So that's what you're seeing right now. On the top and also on the bottom of the picture on the right, you see that there the constraint that the solution is supposed to be, the velocity is supposed to be 0 there, is a little bit relaxed. We're allowing a little bit of slip. And only in a weak sense, and we'll talk about what that means, are these constraints satisfied. And you can already see here from the final solution that the picture on the right is deep red, but the picture on the left is deep red, but the picture on the right still shows a very yellow solution field. And if we then look at the mean flows again, then we find indeed that here now represented by the line in green, that we're able to predict the mean flow very, very effectively. That was by introducing now this ability to slip a little bit. Okay, then I'm kind of moving towards my conclusion here. With the previous two examples, I hope that I've kind of been able to illustrate a thought pattern that I would like to extend pretty much to all the lectures in this class, where I'm not exclusively talking about mathematics, I'm not exclusively talking about computational methods, and I'm not exclusively talking about physics. Rather, I'm trying to motivate these examples, the problems, and also the solutions that we'll introduce as a combination of all these three parts of the pie. So for the example of the Navier-Stokes equation a second ago, we talked about the physics in terms that we're talking about a balance of linear momentum. We saw that in the Newtonian constitutive law was important. Then we had this balance of attraction, vector, the shear. So that's the physics part of the problem. Then we talked about the mathematics, where we talked about this, or where I mentioned this, that the boundary conditions are now weakly enforced. Now, I didn't go into much detail here, so I actually didn't talk about the second and the third point here, but that's something that we will talk about later. So there's some mathematics involved in weakly enforcing boundary conditions, which involves Lagrange multipliers and stability parameters. So this says stability requirement on the parameter beta. As you can see in the equations in the previous slide, there was a parameter involved. So this is more the mathematical part of the motivation behind the problem and the problem that we're seeing. And now that we understand where the problem comes from a mathematical perspective, we have to deal with this somehow computationally, where we need to have not a too tight beta, because then we would get overshoots and undershoots. But rather with our discrete representation, we're trying to get the optimal approximation quality. Yeah, so in that example, we have these three facets: the physics, the math, and the computational method. And I'll try in any kind of example that we'll talk about to kind of touch upon each of these sides, to kind of give you a feeling that when we talk about these kind of problems, we're not exclusively interested in physics, and we should not be exclusively interested in physics. We should also not be exclusively interested in the math, or completely try to focus on that, or the computational method. Rather, to make things work and to understand why things work or why things don't work, we have to think about all these components. And that's, I hope, something that I'll also be able to bring forth wherever that becomes relevant. Okay. Then, lastly, the way that I do set up this class, I already posted a notification on the StudIP page where I'm also addressing these points. So what we'll do is I'll record lectures. I don't think I'll do any live lectures. I did that last semester. I don't think that's quite as appropriate for this kind of for this lecture series. Because with these recorded lectures, you'll be able to manage your own schedule. And I think that this lecture theory is quite tough. You might have to rewatch certain sections a little once or twice, and at the very least you'll want to do this in your own pace, and I think that recorded lectures are more suitable for that. Then I also don't think that having the full 1.5 hour blocks of me talking about mathematical theory is appropriate. So I think what I'll do instead is I'll produce shorter videos, and probably this introduction is one of the longer videos there. I think I'm going towards 1 hour now. So usually I think I'll aim for 20 minutes where I'll try to address one topic. and keep everything concise and compact, so that it makes sense for you to rewatch particular videos if you find that you either misunderstood something or later on you find that you have a gap in your knowledge. And you can find a particular video that is of relevance and rewatch that one, rather than having to manage your way through a 1.5 hour lecture to find the details that you're interested in. Now, a total of time contact hour for this class is set on 3 hours, I believe, so 2 1.5 hour sessions. I don't think I'll give two times 1.5 hour lectures, so the remaining time I would like to use for contact time. So you'll be able to contact me. I will still have to kind of figure out how that works, and you'll be able to ask any remaining questions. Yeah? So that would be in some online setting, and I'm not sure if I want to set the time for that or if you want to keep that flexible. We'll see how that goes as we're progressing. Then homeworks. I'll have homework every 2 to 3 weeks. That will count towards roughly 60% of the grade. With this, I hope to kind of motivate you to stay up to date with all the lecture material, so that you won't have to watch 20 lectures at some point. These homeworks will be very tightly interconnected with the lecture material. In some cases, I might genuinely ask you to write a bit of a summary of something that I've said. So the intent is not that these homeworks will take you 10 hours per homework. There's too many of those. I would even say that for many of these homeworks, I myself would be able to do them in half an hour. Now, of course, that's not a relevant comparison. But what I mean to say there is, it's not necessarily the workload that is very high. Yeah, it's that you have to understand certain things, and that might take you a while. So that's why it will take you an hour, maybe 2 hours or 3 hours. But the idea is not that you have a workload of dozens of hours per homework. Now, I think there might be 1 or 2 exceptions where I want the homeworks to be a bit more involved, and you also get more time for those, because maybe I think that that's a particularly important part. Maybe I want you to code some things. So some of the other homeworks might be a bit more lengthy, but in general, I do not want these homeworks to be of huge size. Now, that's 60% of the grade. The remaining 40% is going to be an oral exam, also probably via some online setting, depending on how things progress. And the idea there is that where the homeworks have tested specific knowledge, the oral exam is supposed to test more of an overview perspective. Yeah, I want to make sure that you have not forgotten about the bigger goal of this class by focusing too much on any one of the details. Okay, that is, I think, my last slide, although I still have a conclusion here. So the course content, we're going to talk about finite elements for computational fluid dynamics. We're going to talk about stabilized methods, discontinuous Galerkin methods, use pressure velocity interpolation pairs, fine scale or turbulence modeling. The grading is 6% for the homeworks, 40% for the oral exams. Learning perspectives are, I want to provide you with a different perspective on finite element methods, a familiarity with the language of computational mechanics, so that you'll be more prepared to read these research articles in whatever direction you're moving. And I want you to realize that the finite element method is a great method, but you also have to be responsible as a user and critical towards the results that you're getting. Now, some notes are on the right hand side that I think are important to address. This is not an introductory finite element class. I'm not going to talk about any one of these 4 points that you have here. I'm not going to talk about quadrature integration. We're not going to talk about the formation of element stiffness matrices. We're not going to talk about the assembly of the global stiffness matrix. I'm not going to talk about nonlinear iteration schemes such as Newton-Raphson. I'm going to assume that that's stuff that you've handled in previous classes, and I'll take that as a given. In many cases, that's not even going to be important for understanding the lecture material, but the lecture material will be on a higher level, so at a level where that is no longer important. Yeah? So a more overarching perspective. So it's important that you are familiar and comfortable with those concepts if you're thinking about taking this class. Yeah, and then the last point here, feel free to ask questions via an online format, sadly nowadays. because this is going to be a tough course. I think that you will learn a lot if you choose to carry it out to the end. But it is a tough course, which means that it's important that you take your responsibility as well to make sure that you understand what I'm saying. I can't gauge that from the camera, so I have to know in a different way. So make sure that you ask questions if things are unclear. Either send an email or schedule an open office hour. Okay, I think that's it for this introduction. This was, as I said, an hour. I anticipate that future lectures will be cut into shorter segments, but I think for this introduction, this is fine. So thank you for your attention, and I'm looking forward to talking to you, hopefully with you as well, for the rest of this class. Thank you.